walks because people were walking in front of trains and cars because they were looking at their phones the entire time. They would just walk headlong into it and people were dying. So little did you know, we all need to wear coats of shame.
Yeah.
That's awesome. All right, well, y'all know how I run finals by now, or reviews. So the entire day, as long as you guys want to stay this morning, is up to you guys on what content you want to review, what you want to practice, what you want to talk about. I leave the entire thing in your hands. Your exam is open. I've had several students take it already. So there's a handful of you that have already done it, and they've gotten me out of their hair and they've moved on to actually having slight summer breaks perhaps, or maybe another class or something. But so what do you guys want to talk about today? You will not need to write code. You will need to read and interpret code though. I think it's kind of a douchey thing to make you write code without an IDE. So until I can get Visual Studio in the testing center, which they have been working on actually. They have some prototypes of it, but we're not there yet.
Are they working on getting SQL stuff in it?
They're working on getting all sorts of fancy stuff in it.
Because that would have been so nice.
Yeah.
That been there before, because
we have a lot of
last exam I had to do SQL stuff.
Oh, I know the pain. I've been there. I remember having to write a C++ program, and the rules were it had to compile and function in an essay box on KiteTester. That was an SOB, I'll tell you what. Anyways, so yeah, long answer, yeah, you don't need to worry about writing code, but you'll need to be able to understand it, read it. There will be a couple of questions where you'll have to explain it, you know, maybe write a small paragraph, some aspects of things. But yeah. Okay, what else? It's going to be the shortest review on record, the way you guys are going. Come in, watch Social Media Garden, go home.
Didn't you say there were supposed to be some sort of essay questions on this? What kind of essay questions are we doing?
There will be an essay related to assembler where I'll ask you to explain a concept to me. Rather than, you know, like clicking a multiple choice or fill in the blank, it'll be, you know, a small paragraph and say, okay, explain why does this work, or why does this phenomenon the way it is. Or if you've been writing your assembler assignments and actually can explain why you've written what you've written, you'll be completely fine on them. If you've been one of the handful of students I've had this semester that have not been writing their own assembler assignments, then you'll be lost on those questions. But yeah, so as long as you've been working on that on your own, you should be fine with that stuff. You guys will be good. Apparently, we've done a really good job this semester.
I then I'd assume it's just exactly like the term concept, except what stuff passes the term on.
Yeah, it's comprehensive. So it's the midterm plus everything we've done after it. It's been fun. Hey, as long as you got my stuff done, that's cool. ARM's an SOB to work with some days. Okay. Error detection and correction. We can talk about those for a minute. Okay. ECC, right? Error code corrections. Now, we talked about 4 different categories in here, right? Error detection and correction codes. What were the 4 different types we talked about? Parity. Okay, parity, Hamming, Reed Solomon. And cyclic redundancy check, i.e. CRC, right? Okay. Now, what was different amongst the four of these? How did they change and how did they vary?
Parity was 1 bit.
Right. Parity allows us to detect single bit errors, right? Can we fix those errors? No, we simply know they went wrong, right? We can detect errors. Okay. All right. What do you remember about CRC? Uses a syndrome, right? And what is a syndrome? Besides the supervillain in Incredibles. Ooh, excellent. Okay. Not burst errors. We can't detect burst errors, but it is a multiple bit error or set of bits that we put on the end of a data transmission that we compare. So it's like parity, but rather than just doing a single bit odd or even, we're now going to do it with, say, 32 bits or 64 bits, or depends on which hashing algorithm you use on how many you'll get. Sometimes as high as 1,000 or 2,000 bits will come out in the end. And then we run the same thing. And that's that syndrome. That's the thing we use to double check with. Okay, that's the result of the hashing algorithm we run on both ends of the data. Okay, now where did burst errors come into play? Only one of these could detect and deal with burst errors. Right. What was a burst error? Contiguously, right. When we have at least 2 bits side by side that have been transposed, then Reed Solomon can detect those, right? Now, what else can Reed Solomon do with those burst errors? Not only can it detect them, but it can also, right, okay. Reed Solomon detects and corrects. Okay, Hamming code, detect, correct, where? Yep. We cannot correct burst errors, right? And the amount of errors we can fix in a given thing is based on what we call the Hamming distance, right? I.e. how much extra data we were willing to throw in it. Now that extra data can get pretty substantial. It's one of the reasons we don't use Hamming codes extensively anymore. They're just too expensive to other methods that we have. Okay, CRC, detection or correction?
With Hamming codes, detection.
No, Hamming does both.
Yeah, I'm talking about Hamming just being able to detect burst errors. You can't correct them, but it can correct other things.
It can correct anything, but it can't detect burst errors unless you have an extraordinarily high Hamming distance or low, like meaning, say for every like 2 or 3 bits, you've appended on 6 bits. So in general, we say no, Hamming code cannot detect burst errors because it's unreasonable to make it able to detect those things. In which case you're screwed. Okay, CRC, detection, correction.
Detection.
Yeah, CRC is detection only. Okay, how about parity? Right, it's detection only. Okay, because we know something went wrong, we just don't know what went wrong. Okay, now keep in mind though, RAID, most of the RAID levels we talked about use which of these methods? Parity. The overwhelming majority used parity of RAID to rebuild the array if data was lost. Okay.
We should go over the RAID again.
Sure, let's talk about RAID, yeah. Let me pull up that chart from your textbook real fast, because that makes it the easiest to see everything that's going on here. Oh, let's see, RAID was... Yep, this is every image in your textbook. Say what?
It's really clear what they all are.
Yeah, and right. Don't you love the naming scheme? Oh, bam!
Wow.
If I was my 8-year-old, I would totally dab at that, but I don't get that. Do you guys? Like the younger generations, it's like we did something awesome, so
I have no idea where that even
I don't get it. But anyways, that was, you gotta admit, that was pretty good though. Straight to it.
came from. Saw it here somewhere. People have started doing it for some years.
And they think it's cool. I have to laugh every time my 8-year-old does it. Like he'll make a cool Lego and then he dabs. I'm like, I don't get this thing. Anyways, we're getting distracted. So let's talk about RAID, okay? Now on RAID, what it's going to be kind of like what you had with your quizzes and your midterm, for example. I'm going to be looking to see, do you know what levels are real, which ones are hypothetical, what are the differences between them? I'm not going to make you like calculate capacities or any of that other big stuff, right? So if we know basically the information in this table, that gives you most everything you need to know. Okay, let's identify quickly though, which ones of these were the real versus the theoretical levels. Okay, we'll put an R and we'll put a T next to them to remind ourselves which one was a real, meaning it's something we use in real world production, versus theory that we use to help us make the jump to the next real world application. Okay,
Theory ones are also kind of used, but it's not.
only in a lab. Yeah, so the theory levels were never really used, were never used in production. In fact, you won't be able, you can't go and buy a RAID controller today that will support them. So, RAID level 0. RAID level 1. RAID level 2. RAID level 3. RAID level 4. RAID level 5. 6. Yeah, it's used in data centers a lot. It's definitely less it's probably the least popular of the real levels we're going to look at, but it is in use. Yeah. Yep. You'll find it especially in places where you want heavy protection of the data, and you're willing to sacrifice a lot of extra cost for drives that aren't used for anything but additional protection. For example, situations where it's not practical to run full backups of your data in several locations. You know, say you're working with, say, 3 exabytes of data. I mean, having multiple copies of that just it's not feasible. So it's not uncommon to see in those types of situations. Okay, RAID level 10, real or theory? That one's real. And DP. Real as well, but very, very limited as well. RAID level 6 and RAID and DP are pretty similar in usage. Let's put it that way. So maybe we put an R/T on that one. You can't see that T. Let's not do that. Okay, so let's talk about what makes each of these levels unique, right? Okay, RAID level 0. Yeah. Right. That's the big idea here, right?
As much data as possible. As much data, as much speed.
Yeah. It's all about just striping multiple disks together as if they were one logical, one big disk itself, right? We call it a logical disk in the end. So reliability there is, because as you guys pointed out, there is no backup. There is zero protection, right? In fact, you've enhanced your risk significantly in direct proportion to the number of disks involved, right? So if you have 5 disks, one fails, all 5 might as well have failed because you have lost the entire array. If one goes down, they all go down, okay? But this is the reason we use it, right? Your throughput scales with the amount of disks you have, right? So if you have 2 disks, you're twice as fast. You have 3 disks, you're 3 times as fast. You have 4 disks, you're 4 times as fast. because we can read and write to all of the disks simultaneously. So the biggest bottleneck at that point generally becomes the bus, that we can't pull the data through the buses as fast as we can pull it off the disks.
How does the speed up work there?
You can't. Well, I shouldn't say you can't. I said generally you don't. Most RAID controllers, in fact, won't support it. Some will, but they do that by slowing down to the least common denominator. Yeah, so generally any RAID controller, the majority of them are going to require the same speed and same capacities of disks that are in an array. There are some specialized controllers that don't, but the overwhelming majority require uniformity. Okay, so how did RAID level 1 differ from RAID level 0? What's the difference between them?
It's just on, instead of striping it across multiple disks, it is literally just pull all the data on 2 disks.
Yeah, mirrors, right?
If you have 2, since the minimum amount of a RAID drive you can have is 2. You have 2 drives, they're both just going to be 1 drive, but it's not going to be the same size.
Yeah,
It's just copy them.
it'll be the size of the smallest disk, right? So because we're holding a mirrored set, 2 photocopies, right? Which in the end gives us really good reliability. In fact, it gives you the best reliability out of any of them, because you're now a full 1-to-1 copy, right? The throughput on that gives you then, your reads are enhanced, right? Because I can read from the 2 disks simultaneously. But what about my writes? It's going to be slower than a single disk, right? Simply because we may have to wait for 2 different disks now to scan and to spin into place before the data can be written. Okay, so writes go downhill, reads go up with this one. Okay, now levels 2, 3, and 4. Okay, all 3 of these introduced the big idea that we brought in with RAID level 5, which was we're interleaving data by striping it, right? Again, but in RAID level 5 we distributed the parity. Okay, 2, 3, and 4 brought us the information necessary and the skills and the concepts to get us to that point, right? Because we began interleaving the data here with striping, but with Hamming code. That's the big thing that level 2 brought in, was Hamming code. But as you guys know, to make Hamming code really effective, we have to put a whole lot of extra data in there, right? And that's one of the reasons why we don't use RAID level 2s. It's too expensive. I mean, to write small files, you now end up writing significantly more data to make it protected, okay? So RAID level 3 said same thing, but now let's use parity instead, right? But and there's the big difference here, right? Is we brought it in as a parity disk, right? Where the parity itself was stored on a dedicated disk, okay? Versus RAID level 5, our real one, is we distributed that across all of the disks rather than holding it just on one disk. Okay, it makes rebuilds faster. It also enhances the reliability. Okay, and then RAID level 4 is we interleave the data striping with one parity disk. Yes. Yes. Okay. Well, and 3 supported multiple parity disks. You could have 2 or 3 parity disks if you wanted, or just one. RAID 4, as we said, will have just one parity disk, and will interleave on blocks rather than on bits. Okay. But as we know, bit interleaving is too heavy, right? Because we don't even address bits, do we, on a computer? We address on block levels, right? Okay, so that was the big idea here. Okay, that's what brought us to 5. 6, what's the difference between 5 and 6? We still use distributed parity, but we're using it twice now. Okay, you get the same, we're storing information twice now. We're giving dual error protection, meaning we're storing the parity information 2 separate places. So the net result of that, the difference between 5 and 6, is it gives us a, how do we say it? A higher tolerance for failure. Let's put it that way. We can support losing an additional disk that we couldn't have in a RAID 5 environment. Okay. RAID 10 is really should just be like RAID 1 plus 0 is what we should call it, right? Because we make mirrored sets and then we stripe within those sets. Okay. So we use both concepts together. Gives us, you know, really good protection. It gives us good throughput, both, you know, in terms of reading and writing. It gives us a really good balance of everything, but it does it at a much more significant cost, right? Let's say you have 8 disks all running at 2 terabytes apiece. You only get half of your capacity, right? Or 4 disks, or right? You have to have at least 4 because we got to be able to have 2 different sets, right? But you get half of your capacity because you're mirroring.
On the throughput, it says that RAID 10 is not as good as a single disk on writes.
Yes.
But if you had, say, 10 drives, then wouldn't that be better than a single disk on drive? It's just not going to be as good as.
Generally, the big limitation that comes in all of these, if you looked at pretty much all of them are not as good as a single disk on writes, simply because now you have multiple disks that have to spin into place. They're not all dead synced together generally. So other than that, if it wasn't for that, we could exceed read or write speed, but because we now have multiple disks that are all involved in the processes.
So say if it was a SSD or something like that, where it doesn't move things to the position.
In an SSD, then yes, we would have the potential to exceed it. But without an SSD, we're stuck in mechanical movements. Yeah.
Isn't that what the video you mentioned to us, the SSD awesomeness or whatever?
Oh yeah, the one from Samsung.
Yeah, it boosted the read and write speed by going into like 20 disk RAID.
He did a 24 disk RAID. Yeah.
Like what we get RAID 0, I'm assuming.
I don't remember which RAID level he did. I'd have to go back and watch the video again. It was a long time ago. I watched that.
I mean, I don't see why they would do anything else.
Well, it was just a show off.
Yeah, RAID and why RAID 0.
But I don't know. You'd have to go look. Yeah.
There's also RAID 50 and 60 technically.
Yes, and they're the same thing as RAID 10, right? They're just 5 plus 0 and 6 plus 0. Okay. You'll find as you get out there are some of those where they mix and match levels. Anytime you see a 50 or a 60 or, you know, anything that's 2 digits like that, just that really is what that means. It's the 2 different levels combined together. So that's one of the reasons, for example, you're not going to see like a 15 is going to be very uncommon. It exists, it's just very uncommon. You know, to put a 1 and a 5 together, there just comes a point where it doesn't make much sense to go down the route of combinations, right? It's like putting ketchup on ice cream. Yeah, you could do it, by why would you? Okay. Yeah. So, but if you know kind of those big basics, those are the types of things we're looking for when it comes to RAID. Any other specific questions about RAID we want to address?
Stupid question because this is just being silly now, but you can buy 3 different RAID things.
I have never seen it. Doesn't mean it's not possible. I've just never seen it. There's also the law of diminishing returns to consider here too, right? And I'm pretty sure you would hit that with there.
All right, fair enough. It was just a stupid
Yeah.
question.
Okay. Anything else with RAID? All right. What's next then?
Want to go over risk versus risk again?
Oh, absolutely. That's a good one because we didn't have that on the midterm. Come on, give me a scroll bar. I want more screen space. Okay. Risk versus CISC. Okay. Risk, what does a risk stand for? Computer. Yeah, reduced versus complex, right? That's the first key that gives you a hint to how they work, right? Is reduced instruction set computer versus a complex instruction set computer. Now, when we say reduced versus complex, what is it really that we're referring to?
Physical circuitry on computer die that handles instructions. So you might see add on RISC, just repeat the add instruction.
Right. So that's exactly correct. Okay, we're referring to the amount of, to the ISA itself, how many physical circuits and supported abilities are built into the die itself on the chip. Okay, so as Brandon brought out, right? For example, in RISC, there would not be a command to multiply. Okay, because that would be a complex instruction. Rather, that we would just use repeated addition, i.e., addition in a loop to accomplish the same thing. Versus CISC, we allow complex commands such as multiplication. Okay. The net result is an ISA. Okay. Which one is a large ISA and which one is a small ISA? What?
RISC can technically have less commands than CISC because you have to go through multiple things because it is complex.
RISC isn't complex, though.
I meant the other. You know what I meant, though.
What I recall from our lecture was that you use more instructions for each program, increasing the amount of storage space you need to store those instructions. CISC uses less storage space to store files and instructions. The reason we use CISC on most modern computers is we started with CISC architecture back in the 80s or 90s when memory was at its most precious. But RISC has the performance advantage over CISC because it takes less time to execute RISC instructions.
Right. Right. So the ISA in RISC is reduced, right? That's the thing where the name comes from, right? Is the ISA itself, the size of it, the number of commands available to it overall. Versus this one is larger, right? Because we support things such as complex instructions. The net result in that, in the end, what it all boils down to is in RISC we have, let's put it this way, we have larger files, reduced runtime. I was going to write smaller runtime, but I like reusing the word reduced to help you remember it. Okay, you end up with larger files. Okay, because it took more instructions, more lines in the program to make the thing do it, right? To give it the instructions. Versus over here in CISC world, we have smaller files. Right? Reducing, though, in the end, smaller files, but generally longer runtime to do the same thing because we have now complex instructions. Now, in RISC, how many cycles does it take to complete an instruction?
1.
Right. That's the reason RISC ends up generally being faster is we are 1 cycle per instruction, right? Versus CISC, it's an unknown. It depends on the instruction. It depends on the data. You could have an instruction that takes 5 cycles. You could have one that takes 1,000 cycles. You could have another one that only takes 1. You don't know. Not on when you run, it's on what you run and what you run it with.
So in RISC, could you technically still have a mul command when doing like assembly, stuff like that? It's just, it's not behind the scenes. It's not actually.
No, because in assembly, what's the relationship? 1-to-1, which means every line of code you write in assembly has to correlate to exactly 1 machine instruction.
Machine instructions can have multiple cycles.
Not in RISC. In CISC, though, they can, yes. Yep. Okay. Does that answer the question? Anything else about these ones we want to go over? Or should we move on to the next topic? Okay. What's up next?
How about mass storage?
In which regard?
I can't remember what mass storage or some question.
Just talking about hard drives in general?
Yeah.
Okay. Woo, come on. I don't know why that won't give me more space, but okay. Come on. There it goes. Okay. Now, hard drives. Okay. What do you guys remember about hard drives? Let's see what you remember first.
Sort of a platter, 2 read-write heads for every platter.
Because if we break it down into the components, right, we have the platter, right, which is then broken down into, what did we call the sides? What did we call the sides?
Oh,
Remember, because we could read-write data to each surface of the disk, okay? And then for every surface that we have, i.e. each side of the platter, we have a read-write head on the end of what? What holds the read-write head? We called that the actuator arm. Right? So if you remember, right, we have, here's a surface. Okay. Here's our little read-write head floating on air. There's our actuator arm, right? It's got the cool little hole in the middle, right? Because how did we control the arm moving like this, back and forth, essentially making it so the disk, the head scans closer in and farther out, right? Okay, and what did we call that whole component? Okay, called that a voice coil, right? By modifying that voltage very finely, it's the same thing that makes your speakers work. Because we're controlling how it moves in and out, we're doing the same thing, but instead of pushing something in and out like a speaker, we're moving something up and down within that cage, right? Essentially, we use rare earth magnet and bypassing a voltage through this, right? Along here, it controls where it fits within the magnet and it moves it, right? We call that a voice coil. All right? What else? What other, that takes care of the physical side. Now let's start looking at the logical side of a disk. If we blow a platter up again here, right? Okay. How is the platter itself broken down? Okay. First off, we had, should make another list over here. We had tracks, right? Okay. What was a track? Yeah, a concentric circle, right? That's equidistant from the center, the entire circle. That's roughly there in the diagram. Not quite perfect, but yeah, what are you gonna do, right? That was a track. Now, how was a track broken down, though? And then we had the tracks were broken down into sectors, okay? We also grouped sectors together, and what did we call that? Cluster. Okay. Now, do you also remember in sectors, they were broken apart? We should write that down. What were the 3 parts of a sector? Think about it logically. If you've forgotten, you can reason this one out. Okay. We're going to need a header to describe the data, right? So we have a header. We're going to need a data, somewhere to store the actual stuff, and then we're going to need Okay. Think about networking.
We need an address? No.
It's the same subdivision the network packet follows. Your header, the data, and then we don't call it a footer, but it's the same concept, right? Footer would be web design. We call it a trailer. The guy at the end, right? Which is where we're going to find extra stuff, you know, like the ECC or parity information or whatever it is that we're using to store it. Okay. Pardon? Yeah, that's true. Okay. We use the three of these to combine along with, if you guys remember, the maximum, or what was it? The maximum response algorithm. You guys remember we talked about that when we watched the video? Obviously you don't need to know the name of the algorithm because I just space cadetted it, but basically where it looks and it scans and it says, okay, based off of all of the possible voltage, or, you know, 1s and 0 binary patterns that could result in this voltage pattern, what was most likely meant to feed that off, okay? Because the disk, because as we've shrunk these magnetic domains so much, i.e. we have made our disk so densely packed, we generally can't actually store the exact thing we're wanting to store anymore. We store approximations, and we use math to figure it back out on the other end. We use math to figure out what you intended, which is really what a computer spends all of its life doing. Makes you feel good. Okay?
Considering we also have Siri that is also trying to figure out what you wanted.
Yeah, except Siri sucks. Out of all of them, it has been proven to be the least effective in studies, but let's not digress ourselves into a virtual assistant. Yeah, they're trying to bring themselves back up because they've slipped so hard. They built everything around Wolfram Alpha, which stagnated because Apple gave up. Yeah, another one. I read about that in the news. I don't remember which one it was either. They're going to have hard time competing, though, with Knowledge Graph and then Google's Tensor AI. That thing's freaking amazing.
Graph Lab was the name of the company. Did you see that Google developed it's like a chip?
A chip specifically built for AI. You see Facebook built an AI that designed its own languages, and they shut it down because it freaked them out when it started writing its own world that they couldn't understand anymore. It went, off. But if you side note, you know, you look at a lot of the leading experts, it's kind of interesting. A lot of them are freaking out about Skynet could potentially be real. Personally, I think it's a little bit fear-mongering myself, but it's Terminator. Yeah, it won't make sense if you haven't seen the Terminator movies. But
robots that are amazing and they help people.
Help people? I don't think that's what I would call in Terminator. They do, yeah. I mean, we could say help people die, I guess. They take over. It's an AI that takes over the world. Yeah. You, sir, are crazy.
I mean, this is what we get. This is what we get for just making shows before their reality. We actually start taking credence to these things, even though they weren't.
Well, but they have the potential to be. It's like, have you guys, I don't remember, side note, Squirrel. You remember when Watson competed on Jeopardy? There was the guy from Utah that was the championship guy. It took him head on. His last answer to his final question was, "I, for one, welcome our robot overlords," after Watson kicked his butt. That's exactly what's happening. Anyways, what's next?
For the code we need to interpret, is it going to be something that we've already, similar to what we've already written?
If you've understood your assembler assignments, you'll be good, right? As long as you could, like, if you could walk through and explain why you wrote various lines, not simply what the lines did, but why on top of that, right? So here's what this line does, and this is why I use this line, and this is why I use this functionality, you'll be completely fine.
Well, I wasn't here at the beginning of
the assembler assignments. I don't really know if you went over this, but what's the advantage of writing to TypeScript, or why are we using assembly?
Okay.
So,
Why use assembly over another language? Okay. Sure, that's a good question. Okay. Let me throw it out to your classmates and let's have a little discussion about that. Okay. What's the primary advantage for assembly? Yep. We use assembly because it's all about speed. When we write in a high-level language, we end up in machine code. We write in assembly, we end up in machine code. The difference is when we write it in assembly, we are in direct control, so we can write machine code that conforms to our specific scenario, versus say you were in C or C++, or heck, we could even do the same thing in Java, or one of the interpreted languages. It's just even worse at that point, right? They have to be compiled for the most general, most broad use case. The net result is, for example, we wrote a Hello World program the first day of assembler. That took us what? 4 lines, 5 lines to do it. In C++, if you were to go write a cout hello world, you just did the cout, the arrows, hello world, it'd take you 1 line in C++. But in the end, because of all of the libraries it has to bring in to do that, all of the work of the compiler, all of the other elements, you end up with a program that's in the neighborhood of 15,000 lines of machine code to get the same result. Use it is all about speed. Anywhere we need high performance, we're going to write an algorithm. Even if it's just a piece of a program, maybe it's just a single algorithm or just one small thing, we'll write that in assembly to give us a lot of speed over writing it in some higher logical language. Look at Roller Coaster Tycoon. That entire game was written purely in assembler. But just in case some, I always one students obsolete. Nobody uses it. Okay, that's not true. Let me show you something. Yeah, lots of places do. This is the TIOBE index. Okay, arguably the most accurate rating of in its calculate it. Okay, but assembly language. Oops. Notice what's happening to assembly language. A lot of people think assembly's old. We don't use it anymore. Over the last 6 years, it's gone up fairly significantly in terms of usage. Took a little bit of a dip at the end. If you look at 16 versus 17, but overall, assembly is on the uptick. We're using it more and more, simply because what are we after more and more? More speed, more performance, especially prevalent as we've gotten. The real thing that's brought in a lot of resurgence for assembly is embedded devices, i.e. your cell phones, your tablets, your smartwatches, things that don't have a lot of processing power, but people want to do incredibly complex things. These the magic ticket, right? That's the secret sauce.
Does Apple let us compile assembly to their devices, or would they?
You can. It's a total PETA, but you can. You do an Android.
They do better than whatever the heck Apple uses.
Swift or Objective-C are your 2 language choices. So better though is I want to. It's easier to write. Better is subjective though, right? Because better in what terms? Better in terms of speed, better in terms of writing, better in terms of memory efficiency, right? That's the thing we run into all things with computer. I mean, that a total soapbox here for just a second. That's the reason we have all of these languages in the first place. Because if there really was just one better one, wouldn't we just do everything in that language? No. Okay. Visual Basic's in the middle of a resurgence lately, and it's ridiculous. I don't know why. Because that is a horrible language to work with. But yeah, Visual Basic's not my favorite. But anyways, okay. But you get the big idea. Okay. We have lots of languages because each language is better, or has different strengths and different weaknesses compared to another one. And assembly is no different, right? We have different strengths and we have different weaknesses that it brings to the table. that other languages perhaps don't bring or don't have the ability to do. There's some things we can do in assembly because we have now direct control of the hardware, for example, to do in Java, or to do in Delphi, or to do in MATLAB, right? We could do it much easier in different languages, okay? So assembly, the big reason we use though assembly is all about speed when we're wanting increased efficiency, because now you're in direct control of the hardware rather than letting a middleman, i.e. your compiler, be in direct control of the hardware. Okay? Does that make sense? Does that answer that question for you too, Reese? Okay, awesome. Probably a lot longer answer than you needed, but it gets the idea across. Okay? It's kind of funny too, just as a side note, while you guys are thinking of your next one, my 1030 class I teach this semester, I've got a couple of students, you know, we teach them Java for the last 2 weeks of the semester. It's their first real programming experience, and I've had several of them that are obviously been talking to uninformed programmers because they're like, nobody uses Java anymore. So I just took a screenshot of this and said, look at Java, tell me nobody uses it anymore.
VisualBasic.net is
It's still the #1 language by a double the next closest language.
VisualBasic.net does it. Why is that?
I don't understand that one, but it's been going through a renaissance of sorts. We've had several conversations about that as faculty, and we're all a little bit shocked. Okay, what's next?
Can you go for a segment offset?
Yeah, week 7. I was hoping somebody would bring this one up because it was the most failed aspect of the midterm exam. And if history is speaking something, it'll be one of the most failed aspects of the final exam too. Okay, so let's talk about all of our decoding, right? Okay. First off, though, what is when we say segment offset, right? What does that mean? Okay, what are these two terms? Because they're concepts that we saw quite a few times later in the semester after we'd introduced it. So what's this idea of a segment and an offset?
Segment where you're starting, offset of where the data actually is.
Right, this is a starting location, and then this is some distance that we go to get to the data from that starting location, right? For example, when we use an array, what type of an addressing scheme do we use, really? The segment offset, right? We use the segment, i.e. the beginning of the array, and then an offset some distance into the array to find the piece of data that we're working with. Mm-hmm. Yeah, the first address. Mm-hmm. Yeah, we use the index in conjunction with the size of every element to generate an offset, and we get to our data that way, okay? Now, in week 7, when it came to segments and offsets and all this different type of data, I want to look at week 7 just kind of broader, right? There were 4 different types of decoding we accomplished. What were they? Let's make sure we all remember them. And we can work a couple examples if we need to. Okay, first off, we have IVT, okay? Now this one, you need to have memorized, okay? Because there's really only the couple of steps to it. There is no key to give you here. Okay? So make sure you're comfortable with IVT. We can do an example in segment offset, and we can do a 20-bit if you'd like to as well. It'll take us just a couple minutes if you'd like. I'm happy to do that, okay? So we had IVT. What other types of decoding did we have? We did MP3. Yeah, we did FAT16 root area and FAT16 boot sectors, okay? Now for MP3 and both FAT16s, I will provide the relevant pieces of the key or potentially even the entire key, depending on what you may or may not need for that particular question, okay? So you don't need to worry about memorizing those. The one that does need to be, only one that needs to be memorized 100% is IVT. Now, obviously, you need to know how to use the keys, right? You need to know, for example, how to locate things using the offset, because that's done differently in a root area than, say, for example, a boot sector, right? Or even within MP3, you need to have those basic spots, but I will tell you where to go to find the information. Okay, it's up to you, for example, with root area to remember every entry is 32 bits, or bytes rather. So you look at just those 2 lines, and that offset refers to the place in those 2 lines rather than the entire table. Okay. Right, MP3, we just look at the 32 bits of the frame header, use a frame sync to find it, right? Okay, as long as you're going through those, as you know those processes, I'll give you the key to help you with those last steps, okay? Now, if we look at, let's look at an IVT question real fast. Come on. Please wait. Yeah, I think I figured out why OneNote was crashing too. I think it's the network is dropping because OneNote is running a new stupid thing on our server on the main campus. And so I think we're having network hiccups that were choking it. Okay.
You can hold down, I know you mentioned that you don't like it when it gets out of proportion.
Yep.
You can hold down shift and select the corners in order to keep it in proportion.
Hey, there's probably a keyboard shortcut, you're right, but oh well, it's done now. Most languages, or most programs, if you hit the corner, the default is to keep it in proportion. You have to hold a keyboard shortcut to change the ratio. Except for Microsoft projects, because Microsoft doesn't like to follow industry standards.
Well,
Internet Explorer is a good demonstration of that.
Word is the exception to that because it's the Microsoft, the one that I use that does keep it in proportion, but all the open source ones like OpenOffice and things don't keep it in proportion.
I don't know. I avoid OpenOffice and all those things because they suck. So let's do an IVT. Okay, we're getting distracted here. So I will give you an interrupt number. Let's pick something that's not on our worksheet. Should we do? Let's do interrupt 17. Okay. So what's the process we follow for IVT? We're going to multiply it by 4x, right? Okay. So how do we do this, though? How do we multiply in a different base? Oh, man, you guys are going to be in trouble. Yeah, we carry on the 16s instead of carrying on the 10s, right? So 7 times 4. See how well you guys remember your math times tables, right? What? Okay, what is 7 times 4, though? Okay, can I fit 28 here? Okay, so I need to factor out. How many factors of 16 we can pull out? 1. What are we left with then? Okay, because we had 20 what? 7 times 4 was 20 what? Okay, if we pull out 16, we're left with? Okay, right, because that was a 12 decimal, so we need to put that back into hex, gives us a C, right? All right, we have a C. 4 times 1 gives us plus the carry in, right? Gives us 5. So what do I do with this 5C hex? That's how we find it, right? 5, 5. Come over C, which is the last 4. So the data we're working with is 8B051002. Right, 0210058B. Because remember, reversing the order of the bytes, not the content of the bytes. Okay, how do we put it into segment offset form?
Pull off a colon in the middle.
Yay, there's segment offset form. Right? Our interrupt was not 1.5. We did 1.7, right? Our off segment offset form is 0, 2, 1, 0, 0, 5, 8B. Okay, how do we take it to 20-bit?
Multiply by base, and add
Multiply what by the base?
segment.
Segment, right. Essentially meaning we put an extra 0 on, right? Everything slides over one spot. Just like if you were to take any base 10 number, multiply it by 10, it just means you add a 0 to the right, okay? Because everything goes over one spot.
Now we just add them together.
And then we add them. So our 20-bit address is 0268B. Yes. If you give me 268B, that is not a full 20-bit address, is it? Okay, and we need a 20-bit address. Okay, make sense?
We'll see.
Well, yeah, let's see what happens between now and when you make it into the testing center, right?
Okay. I had some problems trying to figure out which one to add the 0 to.
Yeah.
That
So-
was problematic.
Yeah. So I would just recommend, right before you go in, or, a couple of between now and when you go into, just if you practice a couple here and there between them, if you're to do 1 or 2 of these in a day between now and when you take it, you should be okay. Okay. All right. Do we have more questions? I'm just trying to decide, are we taking a break or are we about done? Where are you guys at?
How many questions
I don't remember. I think it's 40. I think I put it in this document here too. Yep, 40 questions.
Is it evenly split between before the midterm and after the midterm, or is there more questions from after?
It's evenly distributed across the entire semester. Perhaps the only exception to that is there will be the conversions, everybody's favorite. There's a little bit more of those than, because we did those all semester long, not just in those 2 weeks where we introduced them. They kept with us, so they're a little bit heavier, but every week is pretty well separate, pretty well the same. So about 25% of your exam will be on assembler, because that's roughly how much of the semester we spent on it. It was pretty close to a quarter.
So when you say 25% is on assembler, are these just like multiple choice questions or writing code?
You'll not have to write code, but you will have to explain code. You'll have multiple choice, short answer, and an essay type question to see if you understand it. I believe it's kind of douchey to make you do it without an IDE, so I won't make you write code.
I mean, to be fair, there isn't really any IntelliSense for assembler, so.
No, but you can run it. You can build it. Pardon?
Debugging is a thing.
Yeah. Yeah.
Are you gonna give it like a command to say what's the purpose of this?
So I might give you a command. I might give you a small program and say, what would the end result of this be? What would show up on the screen? I might say, here's a command, tell me what, which of these options describes it, or here's a command, explain how it functions, or here's a technique we use, tell me why it works. Those types of things is what I'm looking for.
Hey, something kind of on topic. If I were to come in, are you going to do anything on Thursday this week, or are we done?
We're done after today.
When was the last day we paid the exam?
Saturday.
This Saturday?
Mm-hmm. Yep, you have the whole weekend. I know this is the last week of regular classes, and finals technically is Monday, Tuesday, and Wednesday of next week, but I thought you guys might appreciate having a little bit more time to study and to take more flexibility on what day you can take the exam. That's why we're running it this week instead.
I heard they're selling old quizzes at the bookstore, is that correct?
If they are, I want names and social security numbers because I'm going to string them up.
Back in the day, 20 years ago, when I was at UQ, they did all that. You could go buy that, like the last quizzes and stuff. You could go buy that bookstore, but that's before they even did any of this online stuff.
Yeah, I'd go through the roof if I found out that.
On the assembler stuff, are you gonna have anywhere where like looking for a nitpicky error in it, or is it all just gonna be like, here's what it is, here's what it does?
Define nitpicky error.
Just like I've had 100 professors that are like, oh, it's the output of this, but it's like missing a column, and that's what you have to find.
I'm going to give you code that will compile. So I'm not going to say, here's a code that doesn't compile, tell me why it doesn't compile, because that's what the purpose of a compiler is, is to say, hey, something doesn't work around this general area, figure it out. I'm not going to do that kind of a thing to you. So I might give you code that builds, but runs, and you have to say, okay, what's the expected result? You know, those types of things. But I'm not going to make it debug code without error messages and, you know, good tools. Because I'm a big believer in, like, that my job as an educator is to prepare you for the real world so you can go out and get a job. And some of that nitpicky stuff you're never going to do in the real world, you know. You're going to have Visual Studio. You're going to have some IDE to help you in the real world. So I kind of don't see the point in testing on that stuff. But that's just my personal philosophy.
Will you take a page of notes again?
So you can take either your textbook or a sheet of notes. It's up to you, whichever you prefer. If you decide to take a sheet of notes, it's a single sheet, 8.5 by 11. You can print on both sides. You can print it out on a computer on 0.2 fonts and use your supervision powers to read it. Or you can write it out by hand. I don't care. Or you can take your textbook. You'd be surprised how small those things can go. Yeah, laser printers struggle to go as small sometimes as the modern inkjets, just because the technologies have changed. It used to be the other way around. But you can go pretty dang flipping tiny. You have to have like a magnifying glass to read it. No, thank you.
Can we take a magnifying glass?
No, you can't. The testing center will provide a sheet of scratch paper for you if you want it. Just ask them for it. I've set the exam up so they can give you a blank piece of paper. They will confiscate it at the end. Likewise, if you take a sheet of notes into the exam, they are going to keep your notes after the fact. So don't plan on walking back out with them. They're going to keep them and throw them away. Recycle them through the shredder. You sell them at the bookstore. Yeah, no. So the exam is timed. You have 2 hours to take the exam. How long you take is up to you guys, but that's the limit, is you get up to 2 hours to take the exam. Keeps kind of the pacing of the questions along the lines of what we've done with the quizzes.
What's the Intel 808 register? Can you go over that?
Yeah, so the Intel 8088 was the register handout. So all of the registers we've dealt with this semester, with the exception of the E's, is the Intel 8088. 8086 just put the extended registers because we went to a 32 bits instead of 16 bits. So when we had the extended EAX, you know, the 32-bit AX, for example, that's the 8086. So I'm not going to nitpick some random register that we haven't worked with, but you should know, for example, AX, BX, CX, DX, and their various sizes, the E or the H and the L as well. So the 32, 16, and the 2 8-bit halves. We're not going to move. Well, I'll pick on some of the other ones in there, but for example, we didn't talk about ESI at all, so I'm not going to hit ESI or some of those. But we did talk about the instruction pointer heavily, so that one's fair game. We talked about the flags register, so that one's fair game. You know, those kinds of ones that we've talked about and that we've used, then that's fair game. But ones that we haven't touched at all, like ESI, EDI, or not, yeah, some of those ones like that, ESP. I'm not going to hit you on because that's kind of a punk move.
Are there upper, so is there H, AH, and AL?
To the upper half of EAX?
Yeah.
No. If you want access to those ones, you just rotate it. You split the bottom half into the top and bring the bottom down. Then you can access it via the 16 or the 8-bit halves. Do what you want to do and flip it back on its head again.
Rotate right.
Or rotate left, doesn't matter. Either way, same diff. Okay, what else this morning?
Is rotating one direction better than the other?
Not really.
A slight difference. I can remember which one you did.
Yeah. No, it's not one. It's not like anding versus XORing. That there is just a real minute difference whether you go right or whether you go left, or virtually the same. Okay. Anything else?
Do a floating point.
Sure. Sure. Let's do floating point. Okay. So let's recap floating point real fast. Okay. What is the basic structure of the IEEE floating point number? Right. So our most significant digit is what? The sign, right? Okay. And likewise, if I were to ask you which bit in a sign integer, for example, controlled the sign, what would the answer be? Most significant. If you tell me first, you tell me left. Is that correct? No. Okay. Because again, computers often don't read data in that direction. First or left would actually be the least for the overwhelming majority of computers in production today. Okay. So we want to say most significant digit if you want points. Okay. I think I've harped on that enough all semester long. We should know that by now. Okay. So our sign is in our MSD slot. Okay. What else? Mantis is down here, right? Or the Mantissa was also known as the significand, right? Okay, and between the two, we have the exponent field. Okay, now the exponent field was how big? 8 bits, and the mantissa or significand was the remaining 23, right? Altogether, because this guy was 1, we have 32 bits in total, right? Okay. I don't want to write 23 x's. So we'll use an ellipse, right? Okay. So let's do an example here. Let's do this. 2, 4, 6, 8, 2 point. Ooh, let's make it negative for fun. Okay, negative 24,682.8625. Okay, so what's our process here? Okay, we need to get the absolute value, right? So what's the we're going to basically treat it as a positive number, for remembering to add the sign back in later, right? Okay.
So now we need to put the two different numbers into our binary / hex values.
Yeah, we need to convert them into binary, right? Now, hex is a great intermediary to look at along the way, because I don't know about you, but getting all the way into the doubles, into the tens of thousands up here, kind of makes your head hurt after a while, right? So let's go to hex, because that's what hex is for here. So how many hex digits would we need to represent this number? 4, right? Because we have 1, 16, 256, then, right? And if we were to have a 5th digit, that would be 65,536, and we're nowhere near that size, right? So we can do it in 4. Okay, which side do I start at? The ones or the 4,000s? Okay, so how many factors of 4,096 can I pull out of here? The what? We're hearing 5 or 6. Okay, we're going to put 6. Okay, so what is 6 times 4096? Survey says? I've got 2 of you saying yes and several other shrugs going, oh. Okay, leaves us with what? 1 what? Okay. How many factors of 256 can we pull out of 106? Nothing. How many factors of, what's this position? Factors of 16 can we pull out of here? 6, okay. Which means we just represented how many? What's 6 times 16? Okay, leaving us a balance of? Okay, how many factors of what position is this one? Okay, how many factors of 1 do we pull out? We pull out an A, right? Which is 10. What the?
Looks like we transposed it somewhere.
OneNote's drunk. Go home, Microsoft, you're drunk. Okay, so that gives us the integer portion of the number, right? Okay, in hex. But again, hex wasn't our goal. What was our goal? Binary. Okay, so what's this look like in binary?
0, 1, 1, 0. 0, 0, 0. That would be 1, 1. Wouldn't it be 1? No, yeah.
0, 1, 1, 0 is a 6. Because it's 2 plus 4.
I've already gone to digits.
Yeah. Okay. So now let's handle the decimal portion. Okay. Using the same concept of positional value, but now dealing in negative powers. Okay. So this gives us 2 to the negative 1, or 1/2, right? 0.5. Can I pull out a factor of 0.5? Okay. So if I have 0.8625, and I subtract 0.5, what's left? Okay. Now what's the next one? A quarter, right? So if I subtract 0.25, what's left?
1.125.
Okay. Can I pull out an 1/8?
No.
What's an 1/8? Okay, we have 0.5, 0.25,
1/8 is 0.125, which is too much.
Okay. How about a 16th then?
0.0625. Well, now 0.055.
0.0 what?
0.05.
Okay, I did this to you on purpose, okay? Because I wanted to talk about this. So what do you do? In the real world, what do we do at this point? Nope.
Use different
You'd have, well, if we wanted to accurately represent it, you're right, we'd have to use another data type, because otherwise I'd have to go to 1/32, 1/64, on and on until I finally ran out of bits, right? Okay. Now, when I thought that number in my head, I made an addition mistake because I didn't mean to make you go insane digits like this. Okay. And I won't give you crazy ones where you have to go 5, 6, 7, 8 digits past the decimal point. I'll kind of limit to around 4 digits past the decimal point. So I'll kind of keep you in this range on the exam. Okay. All right. Because This is what I had intended to do, but I did the math wrong in my head. So 1101 for the decimal point. So let's just change the number, shall we? To make our lives a little bit easier. Okay, so what is that? Let's let you guys do the math this time.
9375. Wait, no, 0.5. Wait, 8125.
Yeah.
There we go.
Yeah. Let's pretend that's a 1. Okay, just so we're clear though. Okay. All right. Everybody with me? Now what? Okay, we call this normalization, right? So I'm moving the decimal point where? Right, we want to move it so that it's immediately to the right of the leading 1, right? Because we're going to drop this leading 1 and all the zeros in front of it, right? When we decode it. So then we just got to count how many times does it take us to get there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14, right? Okay. Now what? How do we turn that bias, that 14, into an exponent field? Yeah. If we add 127, what does that give us? One what? Survey says? Okay. What's that in hexadecimal? Eight what? 8B? Yeah, okay. Okay. All right, okay. Now, do we have everything we need to assemble the number?
No.
Yes.
Yes, we do.
Yes, we do. Okay, what's our sign bit? 1, because the number is negative. Okay, what's our exponent field?
1101.
Okay, what's our significand?
Wait, yeah. It's the numbers that we have left. 1, 0.
Yeah, it's from here all the way down, right? So 1, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, plus however many zeros we need, right? So we just put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 bits. So we need right.
How did you get the first number on the left and that binary string there?
This guy right here?
Oh, the other one.
This one? That is this number.
Oh, okay.
There's a piece of vocabulary one there because we seem to like to put that on the tests. The bias is the small number of what the amount of space is the decimal. The exponent is a large number that you put in the field, which is just not 27.
Yes. Yeah. Because that's the reason I put that vocabulary in there is because, again, when this number was originally defined, the format for it was, they tried to use math terms, but they used them incorrectly. That's why we're trying to change it, for example, mantissa to significand. So when we bias it, that's what we're doing is we're moving the decimal point. Normally, in most mathematical equivalents, the bias would be the 127, except IEEE 754, because they wanted to do what they wanted to do. Yeah. Okay, so We have one last step, and then we're done, right? What's our last step? We are good at math. We're just not good at math terms. Most of us hated math classes. Okay, what's our very last step? We're almost done. Yeah, let's group it into hex, right? Okay, so 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. Okay, so what's this look like? 1, 1, 0, 0. 0, 1, 1, 0. 0. I won't make you do zeros. 1, 1, 0, 1. 0, 1, 0, 1. 1, 0, 1, 0. 1, 0, 1, 0. 10, 10. Yep, it's an A. Hex. So C6, C0, D5, A0. It's that guy. Okay. So then you can also go, we could also go the other direction. Now, in case you guys need more practice with some of that stuff too, I'll show you in Canvas. Okay, for the week where we did those particular things, like for example, floating point was week 3. Okay, there are examples on the various steps here, some videos too, if you need to recap with those, you can. Same thing for signed integers. There's videos recapping those here in week 2. Right here, there's a demo right there, walking through signed integers. Okay. All right, anything else? Okay, yeah, high level overview, sure. So caching, okay. Wow, my handwriting gets sloppy when I'm sitting down.
So it was funny because I heard that. So one of my buddies listens to like audiobooks a lot, and the person who's speaking called a weapons cache and a weapons cache.
Oh, it's like saying GIF. It's GIF, people. Yeah, exactly. We ain't talking about peanut butter. Okay, so cache. Now, cache is unique against all other types of memory, right? Specifically in the way that it's addressed. All other types of memory have their own address to reference the data directly. Caching, though, on the other hand, uses something else. What was it? Right, cache is also what we called CAM, right? C-A-M, or content addressable. Meaning, how do we address the content of cache, right? So when we look at cache, we have to look through the contents of the cache itself to find the thing we're looking for. So when we store something in cache, I now have to store 2 things, right? I have to store the data itself, and I have to store what else then? Mm-hmm. And then some means of locating the original address, right? That means it will store the full original content of the memory address and the address itself if we're going to scan within cache to find it. Okay. Now, on a high-level overview level, we talked about several cache mapping schemes. Specifically, we talked about 3, right? What were they? And anyway. Yes, you are right, Caden. Okay, we have direct mapped cache, we have fully associative cache, and we had n-way set associative cache. Okay, now remember n-way set associative was the other two, essentially making it like a multi-direct, multi-dimensional array of sorts, right? Okay, with direct map to the correct row there on the first dimension, and then we would use fully associative to find it within scan, right? Okay, a little bit more in depth, we use block tags and blocks to solve that to make it even simpler. Okay, to find it, because our job's a lot easier in memory. Okay, now direct map cache meant what? How did we figure out where it went? The what? We're digging back here a little bit, aren't we? Okay, do you remember this? We had, here was Cam, right? There was Ram, right? This guy in direct map, remember, went here. This guy went here. This guy went here. This guy went here. Where did this next one go? Goes here. This guy goes here. This guy goes here. This guy goes here, right? Essentially, we used modulus math to figure out where in the array. It always went in the same class. That address always went in the same block, okay? Because of that, we had a big problem in both direct mapped and fully associative had the potential to thrashing, right? Meaning we are setting ourselves up for constant misses because we are constantly replacing the thing we need next time with the thing we just had to put in now because they override each other. They went to the same location. Okay, that's where we thrashed. We're constantly replacing the value in memory, thrashing. We're changing it, and we're never hitting. We're always missing or frequently missing. Okay, all right. And then in fully associative, we identified a victim block a little bit differently than we do in direct or n-way, right? Remember, the victim block was the one we were replacing. We used that by a replacement policy, such as least recently used, or we had FIFO, first in, first out. Okay, but we could use some of those schemes that we talked about. Now, the other really big thing from caching we need to remember, okay, caching was caching dependent upon the principle of what? Of we had spatial. We used one of those three different types or a combination of types of locality to determine what belonged in cache in the first place, right? Based on where it was in memory with spatial, we grabbed around both sides of the address we were asking for. Sequential meant start that one and grab only going forward what was recently used and what's likely to be used again, okay? And we would use some combination of the three of these principles of locality, right, to figure out what went in RAM in the first place to combine, right? So it took this plus this to generate content, addressable memory. We need a type, we need a scheme, and then we need some type of locality or localities together to put. Okay? All right. Does that overview for you? Anything we missed that you wanted to talk about? Okay. All right. What else do we need to talk about? I think we got a few minutes left.
When you
All of it. I think we've covered pretty well the big things that normally are tripping blocks for students.
We talked about the type of error correction.
Yeah, we did that earlier. Yeah.
Anything I should see on my notes we haven't covered is like.
That was the other thing I was going to say we haven't talked about. Right. So remember with digital circuits, okay, and or not and XOR, okay, and then we had those were the basic gates, right? And then we had several combinations of those gates. What were they? NAND and NOR. Yeah, NAND and NOR were the two big ones. What they are and how they function. You should know the truth table for said gates. You should be able to move freely between those three different types, okay? Doing equations, truth tables, and you know those three things and you know the truth tables and gates, that's what we're after with digital circuits.
You still want us to remember the half adder that you added?
Yes. Yep. So, and then we also you should be able to know or recognize those if you see them. Okay, good question.
We only did the sum of products in this class, right?
Correct. Do not simplify your equations because they will not match, and I'm not going to go through the process of simplification to make them right, okay? Because the only technique we used was sum of products. So just do a sum of products. Because that's the easiest one for us to draw real quickly. Okay, let's say we have a truth table. They need easy way to put a grid. It's close. Okay, so sum of products works by looking for what? Ones in the output, right? So let's say we had an equation that said 1, 1, 1. And we had what do I need here? Right, not A, not B, C. Or not A, B, C. Or A, B, C. That's our equation, right? Okay. Then to make it into a circuit diagram, we simply just represent the various gates, right? We have so two NOTs and an AND. Then we use one OR gate to represent, right, the various combinations. Again, we had a NOT and then an AND. A NOT, and we had an AND. Here we would have an AND. So for this equation, we need how many AND gates? AND gates. How many OR gates? 1. Okay. And then up to properly, right? Okay, or more if you do multiple inversions. Okay. But that's the kind of thing we're looking for. All right. This is an equation, yes. Formally, this would say equals the representation of these. Okay. Cool. Anything else in our last remaining couple of minutes, or are we done? Are you sufficiently terrified?
Yes.
It's not going to be that bad. You'll find it feels a lot like the stuff that we've done after the fact. Okay.
So if we didn't do well in the midterm,
You should be studying harder. Shouldn't be scared, just be studying harder. Now, good study habits, right? So in Canvas, we talked about this at the end, but just as a quick reminder, okay? In Canvas, you've got this, obviously, the final review. What that is I went through each week and I typed a list of the objectives that we covered from that particular week, okay? It's built in. I would also recommend quizzes that you struggled with, right? Go back and make sure you can explain why you missed the question. Same thing with the midterm exam. If you missed a question, you should be able to go back and explain why you missed it so that you know you're better prepared to miss that concept again on the final, okay? Now your final will be a lot like your midterm exam. I built a giant pool of questions related to each week, and it will pull a random mix of questions for that week. So everybody will get the same number of questions related to each week's material, but each of you will get a slightly different exam because you'll get different sets of questions related to that particular material, okay?
Did you post the answers to the midterm tonight?
Nope, it doesn't show you the correct one. It shows you the question that you missed, and then it's up to you now to figure out, okay, what was the right and why did you miss it? I left that off on purpose because that's a good thing for you guys to study. Okay? If you have direct questions, feel free to email me, and I'm happy to answer those, or if we need to get together, or either physically or via a Hangout or a Skype session or something this week before the final to answer any questions, I'm happy to do that too. Okay? All right, good luck on your final exam. Thank you, everyone. If you'll do me one last favor, okay? You'll take a few minutes sometimes between now and Saturday and fill out your, look at those. That allows the dean to say whether he should keep me or fire me. Hopefully it's a keep me situation, but take a few minutes and fill that out, okay? All right, thanks everybody. Thanks for the good semester. I hope to see you in future semesters. Study hard, do well. Good luck. Don't die.